CSIS 2430 is filmed before a live studio audience.
So the big thing I want to make sure we understand before we continue moving on, thing number one, propositional logic, what the heck is it used for? Well, one is for proofs. I mean, that's the obvious big one. But it also can be used in circuit logic. And so we've done part A of the circuit logic business. I've shown you how to represent a circuit with an equation, right? A little bit later, we're going to take that a step further. Before we do, though, we're going to need some other stuff in our tool belt. So the next thing we're going to be looking at here is what's called logical equivalences. Okay, let's look at a few pieces of vocabulary to wrap our heads around what this is all about. Number one, this term here, tautology. Tautology is one of these words that you may have never heard of before, but now you'll hear it in regular, everyday, not everyday conversation, but you'll hear it more regularly. Maybe somebody on the news will use it or something, you'll hear it. But it's a statement that's always true. There are situations, there's a statement, a claim that can always be true no matter what. And then a contradiction is the opposite of that. It's a statement that is 100% always false. Okay? And not like my little silly jokes about, the talent of JB. Trying to not lose my lunch here. He who shall not be named. Nice. But not that we can argue and joke and make claims about whether this band is talented or not or whatever. Those are not contradictions. A contradiction is 100% irrefutably always wrong. And a tautology is irrefutably 100% always right. Okay, then a contingency is something that is neither a tautology nor a contradiction. In other words, it might be true, it might be false, we don't know. Or we do know once we know what the variables stand for. Okay? So what is an example, mathematically speaking, and I don't mean math as in 2 plus 2 or 3 plus 7. I mean the math we've been looking at, the propositions. What's an example of some statement that's 100% true all the time? Well, that not necessarily. No, water is wet. No, I'm talking about some just or mathematically or symbolically, symbolismly. Is that a word? Yeah. Okay, that's barking up the right tree, right? P, therefore P. If P, then P is true, right? That's an example. Okay. There's another one using a similar idea there. How about P or not P? Like that. Isn't that 100% true? So remember the rules when you're looking at this kind of stuff. We're talking about this whole thing being true, right? Well, first of all, P, there's only two possible values it can be, true or false. Okay, let's say it's true. If it's true, that's true. Okay, well, true ordered with anything is always true, right? Let's say P is false. Okay, that's false. Well, if that's false, what is that? True. So it's true to order something. So it's always true, right? P or not P will always be true. There's no other way to look at it. Okay? What about the contradiction? What's an example of that? Say it. P and not P, right? The and not P, right? P and not P. Because it's impossible to have both, right? So think about just from a code perspective here. If X, I'm going to really try to make an ampersand here. Is that an ampersand? Let's call those ampersands, okay? If X and Y. Well, in order for the code here to run, what must be the case? Both of them are true, right? Well, that's the idea here. In order for this whole thing to be true, both that and that must be true. Well, in order for this whole thing to be true, each component must be true. Well, that's impossible. P can't be true and not P be true. That can't happen. Okay? Make sense? All right. So how do we feel about that? The third one, contingency, that's basically everything we've looked at so far, right? Where sometimes P and Q is true, sometimes it isn't. There's no guarantee it's going to be one or the other. Okay. So what questions do we have about this idea? We good? So let's start off with this idea here of dealing with logical equivalences here. And the first one that we're going to do, and it's one of the most popular ones that you'll hear about in this world. It's one of the most common. Popular is not the right word, common, okay? And it's called DeMorgan's Law. And here's what it is. DeMorgan's Law states that the negation of a compound proposition that's using a conjunction, so P and Q negated, is logically equivalent to saying not P or not Q. Do you buy that? We're going to prove it in a minute, but do you buy it just logically? Does it seem right? Let's think about an example. Now remember, this not symbol here is imagine that's not there. Imagine it's not there, and it's there at the top. Sorry about that line there. So imagine it's not here, but it's here. Right? Same thing. They're both exactly the same thing. Okay, I just want to make sure you remember that. So we're claiming it is not the case that P and Q is true. Right? All right, well, let's use some examples here. I'm going to do some shorthand because writing on the screen is a little bit awkward. So I'm going to say that P equals dogs, that's what the D stands for, are good. All right? And I'm going to say that the Q stands for cats are good. Right? Obviously, you'd want a better, well-formed formula that's written out a little bit more cleanly, but it's just a little awkward writing on this screen here, okay? So we're saying P is that dogs are good, Q is that cats are good. So what does this say in that context? Not quite. So just the stuff on the left. Don't worry about the logical equivalent on the right. Right, so it's not true that dogs are good and cats are good. Right? Because if I ignore the negation, I'm simply saying dogs are good and cats are good. And I'm saying, well, no, that's not true. I negated it. That's not true. Well, what does that really mean? If it's not the case that they're both good, then what? At least one of them is bad, right? So in other words, dogs are not good or cats are not good. One of them is bad, or it could be both, right? That make sense? So we can see, I think, from a linguistics perspective and from a syntactical, grammatical perspective, that this makes some sense, right? So we feel okay about this logically and sort of just in English terms? Okay, we're going to look at it in a few minutes with more of a formal way to prove it, but right now we feel okay about it, all right? So next one. Let's go with the dogs and the cats thing again. P means dogs are good, Q means cats are good. So what's that first piece here now saying? It's not the case that dogs are good or cats are good. So before we negate it, we're saying dogs are good or cats are good. But now I'm saying, no, that's not true. So what does that mean? Neither of them are good, right? Does that make sense? Which is what this formula says. Dogs are not good and cats are not good. Okay? So it's saying the same thing. That one's a little trickier to see, but it is saying the same thing as each other. Okay? Okay. To the whiteboards. So this is DeMorgan's Law. What I want us to do on the whiteboards here is I want to prove that they're true in a truth table. All right, let's take a look at the answer here. This is the first one, and I think everybody got it correct. But the goal, obviously, is to make sure that, remember, we're looking at this first one here, that is logically equivalent to that, which means all of these values for every scenario must be exactly the same as these values for the same scenarios. And they are. Okay? Take a look at the next one here. Same thing, right? We're just looking to make sure that those values match those values, and they do. We good? Everybody got it correct, so it should be okay. So here's where it gets big, okay? Remember, I want to make sure, don't worry too much about what you're looking at. We'll walk through all of it. But I want to make sure you know why we're doing this. I'm going to keep saying it. There are lots of applications for propositional logic. One of them, it just makes you a better critical thinker. You have to be a little bit more clear, and you have to think about what you're saying, and you have to be specific. That aside, it's for proofs. It's very good for proofs, and we're going to see a big part of that later in the semester. And it's good for circuit reduction, and you can see it used in the circuit world when designing a circuit. So we're going to look at some examples of that in a minute, but this next stuff is what's going to help us with the circuit design portion of it. So in order to do a proof or to reduce a circuit, you have to know this stuff on here. Now, this is an open book class. You're never going to have to memorize this stuff. Some of it just becomes second nature. Like DeMorgan's law kind of makes sense. We've already looked at that. You can see it right here. We've already done this one, right? And if we've proven it in a truth table. We're happy with that, right? Let's look at some of the other ones, though. Take the identity laws, for example. Wait, I think I have a red border. Yeah, look at that. Fabulous. Now we'll mark that up. Okay. Look at the identity laws. It's claiming that P and true is logically equivalent to P. Well, let's think about that for just a split second. You could plug this in a truth table if you wanted to, but why bother when we can just think about this? What if P is true for a moment? Just think of that. Well, then you have true and true, correct? What's true and true? True. What's P's value? True. So that evaluated to P's value, right? What if P is false? You get false and true evaluates to false, which is P's value. So that holds up. If you have this scenario, you have some, and remember, P isn't just P. P could be some big equation, S or Q, therefore A, B, C, and not Y, right? And true. Well, the true can just go away because it's going to evaluate to whatever that big other equation will evaluate to, right? So I think we're okay with that. And then for the same logic down below, P or false is equal to P as well. Because if P is true or false evaluates to true, which is P's value. If P is false or false evaluates to false, which is P's value. Okay? I did that quickly, but I want to make sure that makes sense. We okay? Good? One nods from everybody? Unless you don't mean it, then don't nod. Good? Yeah? Okay. So that one, we'll check that off the list. Domination laws. Okay. P or true equals true. I think that one's kind of obvious. Anything or true equals true, right? And anything ANDed with false equals false. So I think the domination laws are pretty clear. Okay. The idempotent laws. P or P equals P. Kind of a no-brainer, right? P and P also equals P, right? Okay, I think we're okay with that. Well, we've already used this one, right? Double negation. Not P is equal to P. So I think those kind of make some sense. Now, if you remember your algebra days, you've heard about this next one, the Commutative Law and the Associative Law, or I've heard it pronounced Commutative Law as well. Rubik's Cubers use commutators in solving bigger cubes. But there's the Commutative Law or Commutative Law, and then the Associative Law, and the Distributive Laws. You're familiar with those if you remember your algebra days. Look at the Commutative Law, commutative. P or Q is the same thing as Q or P. Well, hello, right? P and Q is the same as Q and P. Think about that mathematically. 3 plus 1 is the same as 1 plus 3, right? Doesn't matter, okay? So I think that one's pretty common sense here. Associative laws. Now, notice what's happening here. We have a series, let's look at this first one here. We have a series of ors with some parentheses around it. P or Q in parentheses ORed with R is the same as P or with Q and R, Q or R. That's hard to say. Okay, so in other words, if I said 3 plus 1 plus 7, it doesn't matter if I put the parentheses there or if I put the parentheses here, it's going to be equal to 11. Doesn't matter. Okay, that's all we're saying here. Make sense? All right. Next one, distributive laws. We're going to come back to that one. That's a little trickier. And we're going to come back to absorption laws. So we're going to look at negation next, at the very bottom one there. I think this is pretty obvious. And in fact, we talked about these. This is the tautologies and the contradictions, right? The negation, right? Again, P or not P is always true. One of those has to be true. And then P and not P is false. Okay, that was our rules from a minute ago. Now let's look at these other two that we kind of ignored. We're going to look at distributive and absorption. And line up my check marks here. Get them straight, man. Okay, so distributive laws. We know this from algebra, right? We know about this. So if I have this, let's do that plus 3. If I distribute that x, what do I get? Yeah, 2xy plus 3x, right? That's the distributive law. We know how to do that in algebra. It works the same way here. It's a little harder to see, but it's not that big of a deal. So if we take this first example here, we're looking at P or Q and R, right? So if I just distribute it in, I can actually say this or this, right? And this or this. Follow? And the other one works the same way with the ands and the ors reversed. Now, that one, I showed you how it works, but you may not necessarily agree that it does work, that it is correct. I just showed you, logistically, how do you do it? So how would you prove to yourself that it is logically equivalent? Truth table, plug it in the truth table. So any of these logical equivalences, if you're not buying it, maybe the book's wrong, maybe there's a typo, and there are typos in this book. Maybe I'm full of it and I made up this slide and it's not even from the book. I don't know. You never know with me. So if you're not sure, plug it into a truth table. Okay, some of these are kind of obvious, right? But I'm going to say we're good on this distributive law. What about this absorption law? P or P and Q is equal to, logically, whatever P is. So how could we prove this? And we could do it in a truth table, of course. And that's good. That's a good tool to have. But also what we're trying to do here is train our brains to think through these things with, just sort of logicking our way through it, if you will. So here's one way I could logic my way through this. I could just assign a random value to each of these. I could say that P is equal to false, we'll go with true. There's that little half T, half F there. And we'll say that Q is equal to false for a minute. Okay. So at the moment I have true, or it doesn't even matter what's left, because true or with anything is true, right? And we're claiming that whatever this whole thing evaluates to will equal whatever P is. Well, doesn't true or with anything equal true? And so right at the moment, it does equal what P's value is. Agreed? What if P were false? Let's go with that. So let's see if I can change that. P is false. Well, start off here. Now we have false. We have false ORed with something. And at the moment, P is false. So if P is false, does Q's value even matter? No, because P being false right here, ANDed with anything, will always evaluate to false. Agreed? So in both scenarios, it happened to be that Q didn't even matter. Q's value didn't matter. But in this case, we end up getting false ORed with false. Well, what's false or false? False, which is also the value that we said P is. So both scenarios, when you evaluate it, it ends up being equal to whatever P's value is. That little trick is very handy because if you look at what's going on here, and again, use a truth table to prove it to yourself or whatever, but if you look at what's going on over here, if you have this show up in a proof or in a circuit, well, man, you can cut out a whole bunch of crap and just replace it with P because logically it's identical. Feel good about that? Yeah? Let's take a look at this first one here. I'm not going to prove these all in a truth table, and we're going to do this one very quickly, but this is a rule that we'll use quite a bit. And all of these, right? So this whole table on the left here is logical equivalences for conditionals. Something, therefore something. This is logical equivalences for biconditionals, and this is logical equivalences for compound, but they're not using conditionals. So ands and ors, all right? Okay, so we're claiming that P, therefore Q, is logically equivalent to not P or Q. Let's think about that in terms of a sentence first before we look at it in a truth table. Okay? Let's go with our old standby. P equals I won the lottery. Q equals I'll give you $1. Okay? So the left hand says if I won the lottery, I give you $1. I'm claiming that's logically equivalent to I did not win the lottery and I gave you $1. Is that right? Or I gave you $1. Sorry, I apologize. Yeah, thank you. Good catch. I was testing you. Good job. Yeah, sorry about that. So let me say that again. Left side, if I won the lottery, I give you $1. Right side, I did not win the lottery or I gave you $1. Is that right? Because if I did win the lottery, I gave you $1. So if I gave you $1, I probably won the lottery, right? I can give you $1 without winning the lottery. That's still okay, right? But I did not win the lottery, or I gave you $1. In other words, if I won the lottery, you got $1. In other words, if this is false, then this one must be true, right? That one being false means I did win, which means I have to give you the $1. Okay. So that makes some sense here, speaking grammatically, but let's look at it in a truth table quickly, all right? So the first thing we're looking at is we're saying this or this, right? So, and then we're also looking at this, therefore that. So what is the answer to the first row there? What's not P or Q? It's true. What's P, therefore Q? Also true, right? Look at the next one. Not P or Q. False. And P, therefore Q? False, because we started with a true and we did a false, which that's always false, right? And so on down the line, if you look at each one, you will find that they are logically equivalent if you do the truth table logic, right? So that's the only one I'm gonna explicitly prove to you. The group on the right here, we kind of walk through it and we understand them, but we didn't really officially prove all of them.
The next one we did a contrapositive.
Yeah, this is the contrapositive, exactly right, yeah. But back to what I'm saying here, we walked through all these, but I didn't prove them to you all. If you want them proven, do truth tables on them, walk through them yourself with all of these, okay? Every one of these. But the reason I wanted to just show you a few of them is just prove, not in a mathematical term, but sort of convince you that, yeah, they're all correct. Once you believe that, which takes some time to believe it and remember it, then you can do all kinds of stuff when it comes to proofs, all right? We're going to look at some examples of that. To the whiteboards. So the assignment here, the whiteboard thing was, let's take the statement, number one, Miguel has a cell phone and he has a laptop, and then turn it into a negated statement. Now, if you're going to remember one thing from today, this is it. We're about to make a sentence here, and we're going to negate it. But you can't just do that. You can't just, like you're trying to solve some formula, and you can't just go, oh, I think I'll negate the Q. It'll make it easier to solve. Right? That's the equivalent of trying to balance an equation by removing 5 from one side but adding 7 to the other. That doesn't balance it out. Then you have a problem, right? All we're doing is we're negating it just so that we understand how negation works. Because there are legal scenarios where you do negate. Take our freshman, for example. We were talking about being a CS major or not being a freshman. Well, we started with the F equaling you are a freshman, and in order to make the sentence make sense, we had to negate it. But you can't just go around randomly negating stuff and then applying DeMorgan's law to it unless it actually is logically correct, right? I just want to make sure that's clear. So how would we say Miguel has a cell phone and he has a laptop computer? It's a real easy one. No, how would we say Miguel has a cell phone and he has a laptop computer? P and Q, right? Miguel has a cell phone, P. Miguel has a laptop computer, Q. P and Q. That's it. How do we negate it? That's the part you're about to say, Daniel, which is negate it. There, that's not. Now how do we speak that? Well, say the full sentence. How do we say it?
It's not the case that Miguel has a cell phone or.
Not or. It is not the case that Miguel has a cell phone and Miguel has a laptop, right? That's what that negation says right there. So what does that mean? In English terms, what does that mean? Yeah, he may have none or one, but he doesn't have both, right? Yeah, it's not the case he has a phone and a laptop. He might have only a phone, he might have only a laptop, or he might have neither of those, but it's not the case that he has both, right? Okay, so we'll do DeMorgan on it in just a minute, but we basically just did it, right? It is not the case that he has both. So if you don't have both, what does that mean? He does not have a phone, or he does not have a laptop. That is DeMorgan's law applied to that, okay? All right, let's look at the next one. This one's a little trickier, but it's not too bad. Heather will go to the concert, or Steve will go to the concert. So, easy enough to say Heather will go, or Steve will go. That's easy enough. We can also easily negate that. But how do you say the negation now? Yeah. The easy way to read these is throw "it is not the case" in front of it, right? It is not the case that Heather will go to the concert or Steve will go to the concert. Okay? So what is that now? Now that we've said it, let's talk about what it kind of means, which is kind of where you were going in a second ago, Daniel. So what does it mean to say it is not the case that Heather will go or Steve will go? Yeah, it means neither one of them's going. It is not the case that Heather or Steve will go, right? Which means Heather won't go and Steve won't go, right? Which is DeMorgan's law applied to that. That make sense? Okay. So now I'm going to give you a little sort of memory peg to help you, a little mnemonic device to help you remember how that works. We understand it, I think. We believe it. The English sentences make sense. We've proven it's true in a truth table. But now it's just a matter of remembering what the rule actually is, right? So here's one way to do it. There's lots of ways. And when we get into DeMorgan's law for quantifiers, it's a little different, but this works for now. So here's the original. We break the line and flip the sign. Okay? Break the line. Right? I broke the line and I flipped the sign. Okay? Break the line and flip the sign. And it works both ways. If I started with the negation of P or Q, then I break the line and make it not P and not Q. Right? Break the line, flip the sign. So now I could have just told you that from the beginning. Yeah, just break the line, flip the sign. That's DeMorgan's law. But I want you to know that it's true, and know it because you proved it in the truth table, and because you made the sentences and they worked. All right, so we kind of walked through this already, right? We looked at that. There's the negation of it. There's the DeMorgan of it. All right, so any questions about that one? We already walked through it. And then here's the one with Heather. And again, we already did this. There's the negation of it, and there's the DeMorgan of it, okay? So next up, we're going to do our first sort of proofish thing here, okay? This is a very small version of what a proof looks like. I want to prove that the thing on the left is logically equivalent to the thing on the right. Now, what's one we already know how to do? It's the truth table, right? Which would only have two variables, so it would only be 4 rows. It would have, I think I did the math earlier, it's about 9 columns to make this truth table. It's not too bad, okay? But we can also use the logical equivalence rules. So here's our first case to put them into use. Putting them into use, if you don't believe in them, you don't have faith that they work, or you don't have them remembered or whatever, then it's a little weird. But if you believe all those logical equivalences work, then here we go. Here's how proofs work, okay? So the goal of anything like this is I'm claiming that that is the same as that. So what I want to do is somehow magically convert that into exactly that by algebraically rearranging it, if you will. It's not algebraically, it's logical equivalently, but it's the same idea. When you're solving for x, what do? You rearrange things until you get what you're looking for, which is x on one side, an equal sign in the middle, and something on the right. You just keep playing around to get what you want. Now, sometimes you find, well, I can't get x isolated for whatever reason, right? Because it's the equation is too complicated or something like that, right? It's too weird, and yeah, I got it isolated, but the the math on the right-hand side is a nightmare, right? So sometimes it's wonky. In our scenarios, sometimes we can't get to where we want because it can't be proven to be true. But in this case, we'll find out that it's going to be proven no problem. So what is something that I could do? I'm going to start with this thing on the left. And I'm trying to make it become this. So what's something I could do to it with some of our rules that we know about? What was it? Yeah, I could DeMorgan it, right? Because remember, DeMorgan's law is saying when I have something or something else that happens to be negated, or you can draw negation the other way, then I can apply DeMorgan's law to it. Well, I have exactly that. Here's my first something, there's my or, and there's my other something. So I can apply DeMorgan's law to that because the whole thing is being negated. So if I do it, I end up with not P and not the case of that, right? I'm just throwing the negative symbols on there. Do you agree that that is a proper application of DeMorgan's law? Okay, what can I do now? I could distribute. I could take this negative or maybe this thing and distribute or something. And we could try that. The next slide is not that, so I want to walk with the slides. But let's just talk about that for a minute. A lot of times what happens in a proof is you try something out and you may go in a circle and you're like, well, that didn't work. Or, hey, that did work. And there's more than one way to do what we're doing here. So it sort of becomes a little bit of trial and error. One of the things you kind of keep in the back of your mind, though, is that I'm trying to make that look like that. And so I've already I'm sort of got something going on right now that's roughly looking like that already, right? So maybe DeMorgan that out. Because if I DeMorgan that, then I'm going to get my symbols sort of separated. We'll see how it goes. Again, DeMorgan, it might be the right thing to do, might be the wrong thing to do. It's not illegal as far as it is logically accurate, but it may lead us nowhere. It may lead us somewhere. It's trial and error, right? Turns out in this case, it is going to lead us somewhere. So we DeMorganed this whole thing, which gave us this thing in the square brackets. Make sure we're buying into that, right? What's the obvious next step here? There's a big one that's just really easy to get rid of. What do you mean clean it up?
Combine the negative.
Yeah, there you go. The double negation, right? Yeah, I think John said it. The double negatives, right? So that not P in there just becomes P. Okay. So now I've got P I've got not P and P or not Q. Well, we're getting there. Okay. By double negation, we got this. Now what? Don't remember the law name?
Yeah.
And to be honest, I don't remember what the next slide is. I'm actually just using the solution the book did, and I can't remember what the next step. But again, there's lots of different next steps. So let's just take a look and see what it was. Okay. So yeah, we distribute. That's what I thought. Okay. So how does this distribution work? We distributed this, right? And so now I get that ended with P, right? Which is that. And then I get this ended with that, which is this. And then the or sign goes in the middle because that's what's already there. Okay. So what if we distributed and it didn't go anywhere? Maybe this doesn't go anywhere, right? You just, again, trial and error, play around. Okay. So now that we've distributed it, what's the next thing we can do?
First one is like not and P is always false.
Okay, and look at what's going on here. We're trying to get here, right? Look at that. That is that. But we're not there yet because we have other stuff. And this is claiming to be only that, right? So we got to get rid of the other stuff if we can. Also, you can DeMorgan backwards, right? I could turn that back into P or Q negated, but why would I do that? But that is something you're allowed to do, right? Because they're the same thing. But in this case, yeah, you pointed out that not P and P is always what? Yeah, it's false. Okay. So what was our other rule? I think that's the next slide here. It's going to show that. Okay. Yeah. Now, the book takes an extra step that we don't need, and I'll explain why, but we don't need this next step. But what's clearly happening here? What do we know about this? False ORed with something else is what? It's the something else, right? The law was P or false is false, or is P, I should say, right? P or false is P. Well, because the law is stated as P or false, the book rearranges it, right, to give us that or false, but it's the same thing, right? And it is the same thing because of that law right there, right? But that's a step that we could probably not need to do in our brains, right? It's kind of easy. But anything ORed with false becomes whatever the other thing was, based on that law. That was like the first law in those logical equivalences. So that becomes that, the identity law. Yeah, good question. So the question was, where does this negation go? So where did it go with the DeMorgan law here? What we did, so I'm going to redraw this down here. We have P or something. Don't even worry about what's in the something. Negated, right? Well, with DeMorgan's law, remember, you break the line, flip the sign, right? So now we have not P and not whatever was in the parentheses there, right? Yeah. Good. These are good questions. It's good to make sure we got our heads wrapped around this stuff. Okay, so now let's back up to this previous slide here where we rearranged it just because it fits the way the law is worded, but obviously that's pretty clear. And then that just becomes this, which is exactly that. And so the way this works, and this is how proofs work, I'm claiming that this is logically equivalent to that. Well, here's how I proved it. I showed that this, which is our starting point for this thing, is logically equivalent to that, and that that is logically equivalent to that, which is equivalent to that, which is equivalent to that, and so on down the line, until I've proven that all these things are the same. Every one of those rows are identical to each other, and they all equal this thing on the left and this thing on the right. Okay? This is how proofs work. Now, again, we're going to get way more in depth in proofs later in the semester, but this is conceptually how proofs go. Okay? All right, questions on that one? Okay, so this next one, I want to prove that this is a tautology. I'm claiming that P and Q, therefore P or Q, is always true. That's what a tautology means, right? Well, let's just look at it like just, with our brains, not trying to walk through a proof. P and Q. Dogs are good and cats are good. Let's go with those examples. Therefore, dogs are good or cats are good. Well, yeah, if they're both true, then the or is also true, right? I mean, that's really all there is to it. But how do we prove it's a tautology? I'm trying to make this look like that, a true, a T, okay? Well, let's do it real quick, right? So we start off with the original thing, and we're trying to manipulate it and mold it to be true, just a T. So by example 3, and I'll show you what that means in a minute, the little slide will pop up. But we use that first rule that we spent a minute to do in a truth table of the conditionals, where we said P, therefore Q, is equal to not P or Q. Remember that one? Okay, and if you don't, here it is. Okay, the first rule right here. That's all we did. We applied it to that. Remember, P's and Q's, oftentimes in these laws like this, are placeholders for placeholders, right? So, an X in algebra is a placeholder, right? But I could also use A and B and C as a placeholder, and I just refer to these as, some variable X. That variable could be A or B, it doesn't matter, right? That's the same idea we're doing here. We're just saying, I got some P right here. Well, what is that P? Well, in this case, it's that. Maybe it was this and that, I don't know, right? But it's something on the left of that arrow. That's all that means, okay? Bye-bye, beautiful. That's funny, I bumped a little speaker thing on my hotkey there. Okay, so we just applied that law right here. That's all we did, all right? Now what can we do? You see anything? DeMorgan, yeah, always look for DeMorgan, because DeMorgan makes life happy oftentimes, right? DeMorgan's, and here we go, we got one right here, right? And so we break the line, flip the sign, we're going to end up with not P or not Q, right? Now what happens when that occurs? look at our new pattern here. What do we got?
Not all or.
We got all or symbols, right? Okay, we have all or symbols, which means forget the name of the law, right? Whatever the law is, I never remember those names. But yeah, whatever the law is called, you can rearrange the letters and put the parentheses wherever the heck you want. Well, what's a really simple thing that we could do that would maybe become useful? Look at all the variables we have there.
P or Q.
Yeah, we got a P and we also have a not P. We got a Q, we also have a not Q. We know if we group those together, what happens, right? So let's do this. That's totally legitimate by the associative and commutative laws for disjunctions. Totally legitimate, but now I put the P and not P together, the P or not P together, and the Q or not Q together. Well, what do those evaluate to? True or true. Because remember, we're trying to turn this into a true, right? Well, if those evaluate to true or true, well, what's true or true evaluate to? True. The end. We just proved that it's a tautology. It's always true. This will always evaluate down to true. Okay? You could do that in a truth table. If you ran it through a truth table, you'll see all 4 values will be true. You can do it with just plugging in a sentence and it sort of makes some sense, or you can do it a little bit more formally. So what questions do we have about that? Those rules there? Okay, so I'm going to say this again today. Why does propositional logic matter? It makes us better thinkers, number 1. Number 2, it helps us do proofs, mathematical proofs. And why do we care about proofs? Eventually we're going to learn because we can prove that an algorithm's correct. We can prove that a program's correct. We can prove lots of things like that, right? And the other thing we like, besides proofs and better thinking, those are the 2 things. The third thing is we can reduce circuits here. So the output of this, I'm not going to make you guys figure it out, but let's look at it. Would you agree that that's the output? Okay, it's P, and notice this is a triple input here for the OR gate, but it's P ORed with not R, which is coming in right here along this path, okay? Maybe I should change that color from red. And then ORed with not Q or R, which again, here's Q or R comes out and it gets inverted to become not Q or R. So the final output of that circuit is this below, agreed? Okay. So let's take a look at the next one. Could I reduce it? This same circuit here. The answer is yes, and this is what I get reduced. Okay, it's not much, but it's a better circuit. We got rid of that AND gate. Okay, so now we have a better, cleaner circuit. Now, I didn't prove to you that my reduction's correct, but I applied logical equivalences and I reduced the circuit. Once I reduced it, then I've shown it here, and you have to prove that yourself to make sure you believe that it's correct. But assuming my logic is correct, then this circuit is identical to the other circuit, has the same final result as far as whatever the circuit's doing, the voltage or whatever, okay? But it's a cleaner, smaller, better circuit, okay? Look at this guy, okay? This is a lot bigger. Here's the final output. Again, you can pause the video and walk through this yourself to make sure that really is the final output, but it is. Then I can apply whatever rules, logical equivalences here, and reduce it to that, believe it or not. That is a valid reduction of it. That circuit looks like that. Okay? Much better. I got rid of 3 AND gates. Way better. Less wiring, less whatever, less distance between components, all kinds of stuff. Okay? So this is a much better circuit. Now, both of these, I contrived them to go from really ugly to really simple, just because I wanted to prove the point. It's not necessarily the case that you're going to have that occur all the time, where you go from some huge circuit that takes up this whole room to something that fits on your thumbnail, right? I mean, but the idea still holds. Okay, so why does this stuff matter, folks? Propositional logic was our main focus for the past 2 days. We dealt with negation. We got compound propositions, dealing with conjunctions. That's this. Or sorry, excuse me. That's this. Disjunctions. That's that. Conditionals, biconditionals, truth tables, and then we looked at all the notation, which I just basically did. And then we looked at logical equivalences. And those logical equivalences plus truth tables equals the ability to do proofs, to think more clearly, reduced circuits, and a whole bunch of other stuff we'll talk about throughout the semester. What questions do you have about anything we've covered the past couple days?